Okay, now that we've taken a look at balancing, what type of reaction there are, predicting our products, we can kind of go to our last step on will this reaction actually occur? We could write out a million different chemical reactions, but that doesn't actually mean every chemical reaction is going to occur in real life. Okay, and the nice thing with this is we don't actually have to sit and test every one in real life to tell if they're going to happen. We have some ways to go about doing this. So that's what this set of notes is going to focus on. Now, like I said, not all reactions will occur. But there isn't really an easy way to tell on paper if a synthesis or a decomposition reaction will occur. This is only going to focus on single replacement and double replacement reactions because those are kind of the ones that we have a good way of looking at a chart to tell and make a prediction on will this actually occur. Okay, so with single replacement, the single element that you are using to kick out something in the compound must be stronger than the one it is replacing. Okay, so that single thing has to be stronger than the thing that's already bonded in order to take its place. We determine strength by using this activity series, is what we call it, or reactivity list. Okay, so the things high up on this list are really reactive, and the things down low are not very reactive. Okay, so these things are stronger than these things down here. Okay, now we see lithium, potassium, calcium really high on the list. We see hydrogen here all in caps. That's because hydrogen is kind of our comparison. Okay, all of these things up above hydrogen will kick out a hydrogen in water, actually, which is kind of crazy. But the things below hydrogen will not kick out the hydrogen in water. Okay, this is why things like gold, platinum, silver are really good for jewelry because it can get wet and not degrade by kicking out the hydrogen in water. Okay, copper, a lot of like statues and stuff are made of copper, and it won't kick out that hydrogen in water, so it can get rained on. Okay, now notice that we have a list here for metals, and we have a list here for halogens or nonmetals. Okay, our halogens form negative charges. They cannot replace metals because metals form positive charges. So we have to have two different lists. If we have a non-metal, we're gonna look for it on this list, and notice it's a pretty short list. If we have a metal, we're gonna look for it on this list. Okay, so an example. We have a reaction between aluminum chloride and potassium. Now, aluminum chloride is our compound. It's AlCl3. And potassium, K, is our single element. So what we do to see if this reaction is actually going to occur is see, is potassium higher on our activity series than aluminum? Because they're both metals, so potassium's going to try to kick out aluminum. So potassium's way up here. It's the second element on the list. And aluminum is way down here. Not super far down, but down quite a ways. So potassium is stronger than aluminum, which means we can kick it out and the reaction will occur. So a test question, you might get a question like this on a test. It'll say, will the reaction between aluminum chloride and potassium occur? And it might say why. Your answer here would be yes, because potassium is higher on our list than aluminum, which means it's stronger and can kick out aluminum in the reaction. I already mentioned the separate lists for metals and nonmetals. That's really important to remember because these guys over here are not going to kick out any of these guys over here. One last thing. You will get this chart on any test or quiz going forward that you need it on. If you don't need it, we're not going to give it to you. Okay, double replacement. Now, double replacement, we typically look at double replacement reactions as done in solutions. Okay, and solutions are when we take a chemical and we dissolve it in water at a certain concentration. Okay, so that thing dissolved in water are called aqueous solutions. So when we're going to have a double replacement reaction occur, we have to start with two things that are aqueous And then we have to see something happen. Okay, so we have to start with two things that are aqueous, and we have to form one aqueous thing and one solid. Now you might have noticed on some of your practice in chemical reactions B, you had little parentheses with AQs and S's and G's and L's. Okay, those tell us the state of that. So you can probably guess an S is for solid, an L is for liquid, a G is for gas, and then that AQ means that it's aqueous. So if we're doing a double replacement reaction, we need to see AQ plus AQ making, remember that's what my arrow means, AQ plus solid or solid plus AQ. The order really doesn't matter. We cannot have solids on our reactants. We cannot have two solids on our products. Okay, so to do this, you're going to determine if the compounds are aqueous or solid based off a table of solubility. So the table that I have for my students lists S's and AQs. You might want to check with your teacher. They might have it listed as different letters, but the S's typically mean that it's a solid. It's insoluble. It's not going to dissolve when placed in water. So in our reaction, it will form what we call a precipitate, or a solid that is just kind of floating or sitting at the bottom of the water. If a compound is listed as AQ, it means that it is soluble in water, which means it will dissolve when placed in water, and we will not actually see that compound in our solution because it'll be dissolved in there. Now, it might lend a color to the solution. For example, copper compounds, when they're dissolved in water, are blue, but it will not actually be seen. We can't actually see the particles. Okay, so here is your table. Now this one is a screenshot, so it has all the misspelled things for the AQs, so it's kind of hard to see. But like I said, S's mean insoluble, does not dissolve in water, a solid forms. AQs mean aqueous, it's a solid that dissolves in a liquid. Okay, so we use this like a multiplication table. All of our cations, or our positive ions, which happen to be metals, are all down the side, including things like ammonium, which is our one positive polyatomic. Across the top is all of our anions, or our negatives. Many of these are halogens, bromide, chloride, iodide, and then we have a lot of polyatomics in here too, acetate, carbonate, chromate. Now this is not a complete list. Okay, there are a lot of other compounds we could form out there, but these are the most common ones. This is what we will be using. Again, you will get this table on any test or quiz that you need it on. Now, we use this like a multiplication table. So if I have ammonium chromate, I'm going to find ammonium, and I'm going to go over to the column that's chromate. Now, it has an AQ in it, so that means ammonium chromate will be an aqueous solution. So I could put parentheses AQ next to my formula for ammonium chromate. If I went to calcium carbonate, okay, that's actually the formula for chalk. Chalk does not dissolve in water, so I'm expecting to see an S here, calcium carbonate. Yep, solid. Now notice that iron, we have an iron 2 and an iron 3. Remember those parentheses with the Roman numerals from way back in our matter unit? Those tell us the charge. Okay, so iron with a +2 charge is different than iron with a +3 charge. Okay, so you're going to have to make sure you look at that, because in some cases, like here with iodide, iron +2 iodide is aqueous, but iron +3 is solid. Okay, so it can have some differences. Again, this isn't an exhaustive list. It just has the ones that we will always be using. Now, an example here. Calcium nitrate and potassium phosphate react together. So we're going to come up with our formulas here. Calcium nitrate, potassium phosphate, and we're going to switch partners. So the potassium goes with the nitrate, the calcium goes with the phosphate. I transferred over my charges and I crisscrossed. This is not balanced. Again, if you're struggling with balancing, this would be a good one to go ahead and try balancing. So I'm going to look these up. My calcium nitrate is aqueous. My potassium phosphate is aqueous. My potassium nitrate is aqueous, but my calcium phosphate is a solid. So I have that pattern that I'm looking for. The aqueous plus aqueous makes an aqueous and a solid. Now, you do need to check all 4 parts, okay? Don't just check the products and make sure that one is a solid, because if you have a solid on your reactants, it's not going to happen. Okay, don't just check your reactants and make sure that they are both aqueous, because you have to form a solid in order for this reaction to occur. So the reaction occurs because it meets our criteria or our pattern. The aqueous plus aqueous makes an aqueous and a solid. Now remember, the order of the aqueous and the solid don't actually matter. Okay, you will be expected to indicate if the reaction will occur for single and double replacement reactions when asked. So like I gave that example before, be ready to not only say yes or no will it occur, but also explain why. Whether that's we have two aqueous things making an aqueous and a solid for a double replacement, or talking about the strength and the reactivity of our different elements when we're talking about single replacement reactions. As a quick review, synthesis and decomposition reactions, we don't have an easy way to tell if they're going to happen, so we won't ask you that. Combustion reactions pretty much always occur. If it's able to be burned, it's going to happen. So we also won't ask you about those ones.